Okay, let's start. Good afternoon. So this week we're going to really switch over to dynamics and fractals, but we had this theorem about the inheritance of completeness for the hyperspaces. And even though it is rather technical, I think the argument is nice and I think it is instructive. So I wanted to go through the proof, and we will do that today. Before I get to it, let me mention this exercise. It's a hard exercise, but it's a nice one. So if I have two metric spaces x and y, and if I have a continuous function from x to y, then the induced map on the hyperspace level itself is continuous. So this is what is called the functoriality of H. So somehow you want to think of this thing something like a function, and basically a functor is sort of like a function that changes, that transforms one context to another one. So this is just some name, but this is sort of like the basic exercise. So you want to take a sequence of subsets here that converges to some subset, and you want to say that the images converge to the image of the limit. Okay, I just wanted to mention this. Okay, so we're going to sort of factorize this whole theorem of completeness into different pieces so that it is rather straightforward, easier to follow, let's say. So here's a first definition. If I have a metric space that is arbitrary, I'm not saying complete, and if I have an arbitrary sequence of subsets, doesn't need to be compact, doesn't need to be non-empty, then I define this object, which is called the inner Painleve-Kuratowski limit of the sequence, which is a subset of x. And that subset consists of all those points that are the limits of sequences that you obtain by sampling from the sequence of subsets you have. Recall that this definition, so this really means that for any n, xn is in an. I'm just abbreviating it. So this is sort of like intuitive in a sense, because you have a sequence and you want to say something like the limit of the sequence of subsets should be the subset of the limits. Okay? So let me write it like this. Should be the set of limits. That's the intuition. Now, here's a first example. Now, you can define this, of course, but at this point, in this generality, you can't even say that this is a non-empty set. So, for instance, here's an example. And recall that our first sort of playground is, or rather the second perhaps. First is sort of finite sets, second is reals. I'm going to consider x to be R, and let me define this sequence. Let's say n plus 1. Okay, so how does this look like? So this is 0, let's say. This is 0. And so this is I guess 0. Then this is, maybe I should use a different color. This is A1. And then this is A2, and so on. Any ideas as to what is the inner pk limit of the sequences. It has to be the empty set, okay? So why? Because the definition of this set is the limits of sequences that I obtain by sampling from each one of them. Well, if that is the case, then what I need to do would be something like this. I take one point here, another here, and so on, and I want that to converge somewhere. But clearly, this cannot converge to anywhere. Okay. So that's why the limit, inner limit is 0, is empty set. Any questions about this? Okay.
There's no notion of the limit not existing. We just have, like, the empty set is the closest thing we can say.
Yes, yes. I mean, the empty set is a perfectly valid subset of X, after all. Yes?
So I just want to get a little bit more intuition, because when I was reading through the thing earlier,
Yes.
today, when we had this for all n x of n is in A of n, is this sort of similar to the picture you drew last time where
Yes.
there's a whole bunch of boxes? There's a sequence in every one, you find a sequence for every single box?
Yes.
Okay. Just want to double check that.
I'm making a sequence by choosing each, so that I'm building the sequence so that the nth term of the sequence comes from the nth set.
Interesting.
Okay, so for instance, this would be x0 and then x1 and then x2 and so on. Okay. Okay. So now we're going to do a bunch of proofs. First, I'm going to have a bunch of propositions. Oh, let's first start with this extension lemma. I had stated this last week, but let's repeat it. So instead of looking at arbitrary sequences of subsets in a metric space, we're going to rather look at sequences in the hyperspace, meaning that each term at the very least should be non-empty and compact. And we're going to really focus on Cauchy sequences and how does the inner limit of Cauchy sequences look like. That's sort of like what we're going to use in the completeness. So X is an arbitrary metric space. I take a sequence in the hyperspace, a subsequence of A. I can do that. And let me take points from each of these elements in the subsequence. So that this X prime bullet is a sequence in X, after all. If A bullet is Cauchy, now relative to the hyperspace metric, Pompeiu-Hausdorff metric, and this sequence of points is Cauchy, then there is a Cauchy sequence X bullet in capital X that is a supersequence of the sequence that I chose, and it tracks the original larger sequence of sets. Such that X prime bullet is a subsequence and X bullet is in A bullet. So you start with a subsequence of sets, and you have somehow a sequence inside that subsequence. Then you get to extend your subsequence into a larger one. Okay. So here's a proof. And again, let me just draw this picture. This is now my time. and I have for each time unit one set. These are the A1, A2 sets. So I drew this. So now I want to have a prime bullet. So that means that it's a subsequence. Let's say that this is my subsequence, okay? Something like this. So this is something like this, right? So A1 prime, this set is the same thing as this. This is A2 prime, and so on. I'm just skipping some of the frames. You can think of it like that. And in the statement, I'm also assuming that if I just focus on the subsequence, for each term, I have one element. x1 prime coming from this, x2 prime coming from this, and so on. The statement is saying that if the sequence of subsets is Cauchy, and if the sequence of points is Cauchy, then I can extend the sequence of points into a sequence of points by sampling from each one of these. Okay? So I want this, 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 this. Okay? So let's be more specific. So there's an increasing function. Let's call it iota, or I, from integers to itself, such that a prime n is the same thing as a I of n. So for instance, in this example, I of 1 is 2, I of 2 is 4, I of 3 is 5, and so on. What is important is that I of n cannot be less than n, because for each n you're going to have to choose one. So you have to be, like going forward. That's the idea. So now I'm not going to draw this again, but now I look at these. Let's say somewhere here is I of 1, somewhere here is I of 2, somewhere here is I of 3. And I need points for each of these sets. And I have a point here. Okay? So, consider this. I'm looking at the set to point distance. So basically what I'm doing here is that I look at this point and I look at its distance to the first set. Okay? Maybe I should draw it here too. So this is A1. This is A1, this set, and here I have a point, and I'm looking at the point to set distance between these two. Now, we had before in one of the exercises that if I were to fix a point in a metric and leave the other entry open, that's a continuous function. In fact, we show that it's Lipschitz. And you're looking at the image of a compact set under a continuous function. Now, it turns out that any continuous function defined on a compact set attains its minimum. then there is an A in A such that f of A is the minimum. Maybe I should say A0, minimum of f of A, where A varies over A. Okay, that's an exercise. So that means that, recall that the definition of this is so I have x1 prime fixed, and the other one is varying over this compact set, which means that there is a point in A1. Let's call it x1. I'm not saying it's unique. Maybe there are multiple, but there is one. Such that the distance between these 2 points is exactly this set point distance. Pictorially, I was looking at the distance of this point to the set. Well, it should be something like this, right? So I'm choosing this point, basically. I can keep going like this. There is an x2 in A2 such that this distance is the same thing as this distance, and so on. This way, I was able to build, I'm starting to build the sequence as you see here. So I chose this point, and then I look at the A2. The distance of A2 to this point that I have already. Pick a point in A2 that minimizes, that actuates that distance, all the way up until I hit this time. And if I hit I of 1, the first time in the subsequence, I'm going to pick exactly this point. Okay? That's what it says. And then if I want to keep going, so how do I come up with a point in the next set? Well, now I'm comparing it to this guy. After all, I have a point chosen in the second element of the subsequence, and so I can compare this set, and I can look at the distance of this set to that point, find a point in here that minimizes that distance, and so on. Let me not write it. As you can see, this gives a sequence such that each term is coming from one of these sets. So this builds. Okay, I didn't write this formally, but if you want to sort of like handle the indices, you can write it. Maybe it's a good exercise for you to write it actually, but we have so much stuff to do that I don't want to sort of spend too much time. Any questions about this? Yes?
Yeah, how we guarantee the existence of a point that fulfills that, I guess, distance in like say A4 before we get to I of 1? Like, how do we know we can select a point that has the same distance away? So if our first element of the subsequence is, say, the fifth element of the regular sequence,
yes.
The third element of the original sequence, how do I know that there's a point there that I can choose that matches the distance?
Oh, okay.
Does that make sense?
It's about this exercise ultimately.
Okay.
Exercise. So let me be more specific. So A in this exercise is going to be one of these sets, and I'm fixing one of these points. Then f of, let's say, y, which is d of x comma y. This is continuous.
Okay.
Now I'm thinking of this function restricted to this compact subset. Then there's a point where you get to minimize. This is the same idea as we had talked about this in the context of this proposition that any continuously differentiable function on the unit interval is Lipschitz. Right, so we had this interval and we have a continuous function. Well, it has a minimum, of course. And it takes it here. Maybe it has multiple minima, but at least it has one. It's the same idea, really. This is just more general. Yes?
So when I was reading through this, the main thing that I felt weird about was you keep starting at the specific x1 I.
Yes.
I guess I'm trying to figure out exactly why it's doing that to construct this sequence.
Well, basically that's all you have. So the original sequence that you started with, that you're trying to extrapolate basically, is Cauchy. So it's a nice sequence, okay? And the sets themselves, the large sequence of sets itself is also Cauchy. So you're basically tethering the larger sequence onto the nice sequence that you already have.
Okay. Actually, by construction of the thing, that makes sense.
Yeah. Now, at this point, then maybe I should say something about that. Once you build this sequence, this x prime, now what we need to do is we need to say, I erased it, but the statement said that it is Cauchy. Without dealing with the epsilons and deltas, let me try to take the distance between 2 points, 2 elements in the sequence, and try to bound it by something that I know is that I can bound. So I'm going to look at this and then this. I'm taking the nth term and then n plus pth term, and I want to bound it by some term that doesn't depend on p, but might depend on n. Right? That's the point of Cauchy. Well, how did I pick the nth one? I picked the nth term by looking at the closest term inside the subsequence. So, or I can do like this, okay? Xn. Okay, these indices are not very nice, but this basically is the idea. I don't want to sort of spend too much time on index management. Okay, I use a triangular inequality. Now, I know that this is Cauchy, so this sequence, it's a subsequence after all, that I started with, that was Cauchy. I can bound this. And these terms are bounded by Hausdorff distances. And plus p and plus p. Oh. Okay. I chose my sequence, these elements, in such a way that this happens. Okay? Because recall in the Hausdorff, the definition of the Pompeiu-Hausdorff distance between two sets. Well, you're going to take these and then you're going to maximize over x1 primes, and then you're going to take another maximum. So certainly, this is going to be bounded by the Hausdorff distances. Well, I know that the sequence A is Cauchy, and I of n is after n. And likewise, I of n plus p is after n plus p, which means that for epsilon, there is an n such that for n after n and for any p, this is bounded by epsilon over 3, because A is Cauchy. This too is bounded by epsilon over 3. And this too is bounded by epsilon over 3, which means that the whole thing is bounded by epsilon. Okay. Questions about this? I know I sort of like fast forwarded this, but we have so much stuff today. Okay, so that's the end of the extension lemma. So you get to extend things. Now, next proposition. Let's call it proposition A. If I have a sequence of elements in the hyperspace, so compact non-empty subsets, then its inner pk limit is going to be closed. It might be empty, like we discussed in the example, but the empty sets are closed, so that's not a problem. Proof? So let me just abbreviate this by A infinity. There's nothing to do if A infinity is closed because closed sets are, as an empty set is closed. So without loss of generality, let's assume that it is not empty. Later on, in the proof of the compactness, we're going to have to prove that indeed this is not empty. But for now, in this generality, for the purposes of closeness, I can just, that is something that is there. So what do I need to do? I need to take a sequence in this pk limit that converges to some point in x. I need to show that the limit point, x infinity, is in fact in A infinity. So I am not able to escape the set by taking a convergence sequence. Now that means that this is a sequence, this x prime is a sequence of limits, right? Because for each, let's say m, x sub m is a point here. That means that by the definition of this, for each m, there's a sequence that converges to xm. So let me denote it by x sub m comma bullet. It's a second index now. Coming from the sequence of sets such that, maybe I should write it like this. Limit as n goes to infinity of x sub m comma n equals x sub m. The picture is, of course, this. This is my A1, A2, A3, and let's say this is A infinity. And I have here x1, x2, dot, 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 which converges to some point, which is x infinity here. And I have that there is a sampled sequence that converges to this guy, yet another sequence that converges to that guy, and so on. So x11, x12, x13 is converges to that. Then I have x21, x22, x23, which converges to the second term, and so on. Now I have a bunch of points, okay? Somehow, let me finish. Somehow I need to be able to sort of pick one thing from this, another thing from this, another thing from this, and so on, in such a way that it converges, that sequence converges to that limit. Yes?
I'm just thinking to explain the notation for the two subscripts a little bit more.
Yeah, so, okay, so x sub 1 is here, okay? But by definition, x sub 1 being here means that there's a sequence I can get by sampling the sequence of sets that converges to that one. But that sequence obviously depends on the index.
That makes sense.
Okay, so for each index m, there's a sequence, which probably I should be using a second index. That's the idea. Okay, this is just some index management, but this is like part of like analysis. Okay. Now, maybe I should have written it like this. And in particular, you see, what is important here is that the speeds of convergences of each of these sequences that I chose might depend on m. Okay, so it's not uniform in m. That's the problem. But still, opening up the definition of this convergence, I have that for any epsilon, there's an m such that for any m larger after that m, I have that the distance between the two is, let's say, epsilon. Okay, let's do this. I'm going to be fast here. This is the definition of this limit, right? That's what that says. But then I can keep sort of taking smaller and smaller epsilons to get a subsequence of this sequence such that I have nice bounds. So let me write it here. For any k, there is some m sub k such that the distance between the limit and the m sub kth term of the sequence is bounded by 1 over k. So you see, this is like a qualitative thing. If, in a sense, for any epsilon, I have this blah, blah, blah. But I can also get specific convergence rates. And I want this mk to be increasing. So okay. So how did I get this? From this statement, I said, let epsilon equals 1. There is some m sub 1 such that after that, the difference between these two is bounded by 1. Then choose epsilon equals 1 over 2. Choose an m after the m that you chose before, such that after that new m, the bound is 1 over 2. You keep going like this, and that gives you a subsequence. Okay, so let's call that x prime k. So that I have a subsequence here. Okay. Now, for any k, instead of using the m index, I'm using the k index now. Now I'm going to use the definition of this sequence converging to that. Okay. That means that there is some, I guess, n sub k, such that after that, I have that the distance between, so prime k and, maybe I should use this notation. Yeah, it's better. Okay. So what am I doing here? I chose a subsequence here. Let's say the first term here is x sub m sub 1. Okay, so I look at the sequence that converges to it. There is some n that depends on k, but that's not a problem, such that the distance between this and let's say here is bounded by 1 over k. And then the distance between this and that is bounded by 1 over k as well, which means that the distance between this guy and this guy is bounded by 2 over k. So if I were to look at d of x sub m sub k, comma n sub k, and x infinity, by putting this guy in between, using the triangular inequality, I have that this is bounded by 2 over k. Okay, that decays by k, which means that it converges. Okay, and so I can say something like y sub k is equal to x sub m sub k, comma n sub k, which is a term in a sub k.
What's the 3 terms in the d function?
Oh, it's not 3 terms, it's 2 terms. This is the term I get here, and I choose the nice guy from here, which has 2 indices, that is 1 over k close.
So that's x sub m sub k comma.
Yes, yes,
2 indices
yes,
indexing x.
yes. I feel like I'm losing you guys. Let me just draw a picture. Let's say, all the way here. So in this limit set, I had this original sequence, x1, x2, and so on, that converges to some point in x, not necessarily at this stage, in a infinity. I sample it to get a subsequence of that sequence in such a way that if I have x sub m sub k, that is not more than 1 over k distant from this limit. So I have explicit bounds. Now, given this, I look at the sequence generated by sampling from the sequence of sets that converges to this. I have that because this x sub m sub k is in the limit set. Okay, so I look at this guy. So this is x sub mk comma 1, then x sub mk comma 2, and so on. This sequence converges to this. But because it converges, I know if I wait long enough, in this notation it is a sub n sub k, so that I have here x sub m sub k comma n sub k, which I denoted by y sub k over there. Well, I know that if I wait long enough, this is going to be bounded by 1 over epsilon as 1 over k as well. If the distance between from here to there is 1 over k, and from here to there it's 1 over k as well, that means that the distance between these two is bounded by 2 over k. 2 over k is it decays by k if I increase k, which means that the longer I wait, the closer I'm going to get to this. Or in other words, given epsilon, I can wait long enough. There is some k such that 2 over k is less than epsilon. That's the idea. I understand the sort of logistics of the indices are sort of kind of complicated, but the idea, as you can see, is not that complicated. Like, you have a bunch of things that converge to this, and for each term here, you have a bunch of things that converge to that. You should be able to sort of like figure things out in such a way that you can sort of like choose this diagonal sequence in a sense. Yes?
So I just want to make sure we're going for each of our blue points on the left-hand side of the right board. We're going far enough in the sequence of
Yes.
that ace of whatever to
Yes.
get 1 over k closeness to
Yes.
the same element. In
Yes.
infinity? Okay.
Yes. And that is why you see it, how long you should be waiting for the horizontal sequences depends on k, after all. Maybe you have to wait more and so on. But you can always wait more if you want. And that's why you can take a subsequence. Okay. Any questions about this? Yes.
So didn't we want x infinity in RA infinity? Like,
Yes.
so we're just saying whether or not it is right now, we can still do this.
Well, what does it mean for x infinity to be in A infinity? By definition, it means that I can build a sequence that converges to it
Yeah.
by sampling.
Yeah.
Okay, I did that.
Yeah.
Oh, I did not do that. Good enough. Good. So this guy is a sequence. Okay, this is wrong. So, okay, so y sub bullet is a sequence, but I did not get a sequence by sampling from each and every single one of them. Okay, I looked at the subsequence of the sets, right? Because y sub k is in this. Okay, okay, but y bullet is a sequence that converges to some point. Convergence sequences are Cauchy, which means that I was able to come up with a sequence from a subsequence of sets that is Cauchy. I guess I need to also assume that the sequence of sets that I started with itself is Cauchy. If I didn't write it, I should have written it. But in any event, once I have this, extension lemma says you can extend it by the extension lemma. X infinity is in A infinity. Okay. So now it's done. Questions?
So if we get that our subsequence
Yes.
is epsilon close or 1 over k close,
Yes.
Is it because A infinity is a compact set that we know
You don't need that.
you don't need that?
No. You need that you have a sequence of compact non-empty subsets that is Cauchy. Let me state it again. That was a statement. That's what I meant. Yes. Yes. So you see, we have that the limit set, which is this pk limit, is a closed set. I'm not saying that it is empty or non-empty. We had to assume that it is non-empty at this stage because otherwise there's nothing to do. Empty sets are closed. And I'm not saying that it is compact, but I have that it is closed. Now, next, I want to show that it's also totally bounded. Okay. So that was proposition A. Proposition B is the same situation. I have a sequence of compact non-empty subsets that happens to be Cauchy. Then the pk inner limit is totally bounded. That's proposition B. Then the pk limit is totally bounded. Oh, by the way, this statement is true for any sequence. Doesn't need to be Cauchy, doesn't need to be in the hyperspace. The limit is always going to be closed. And I've written some notes and it's on Canvas, so it's one of the exercises. It's just that it's slightly more different, the proof of it, because we don't have extension lemma at this stage, if you want to sort of do this more general thing. But in any event, I just wanted to mention that. So, okay. We have closeness. I also want to say that it is totally bounded. And so that doesn't still imply that the limit is compact, because that factorization theorem does require that X is complete, right? I'm not saying that X is complete for either one of these statements. So, proof. Say otherwise. Then there is some epsilon 0 and a sequence of points in A infinity such that the pairwise distances between any two terms is bounded from below by epsilon 0. Okay. Oh, before that we need to prove something else actually, because we're going to use that other statement. So I'm going to change this. This is true, but we need something else for that. Then I'm going to do this. Sorry. So this is like a tail statement. Then for any epsilon, there is an n such that the pk inner limit of the sequence is included in this sequence, in this set. I'm taking the epsilon balls of the terms, let's say like this, and I'm going to intersect like that. Okay, that's what I meant. Total boundedness is going to be a corollary to this. So for any epsilon, if I wait long enough, then this pk limit is inside this intersection of balls centered at set terms. Okay, proof. Maybe we should take a break before. Okay, 5-minute break. When we get back, we're going to prove this. We're getting this. We're getting to the proof of completeness step by step. Let's take a break though. Okay, welcome back. So let me state this again. If I have a Cauchy sequence of compact non-empty subsets of x, Cauchy relative to the Pompeiu-Hausdorff distance, of course, then we have this inclusion statement. For any epsilon, there is some integer n, capital N, such that the pk inner limit is included in this intersection of balls centered around the terms of the sequence. And you know, instead of writing it like this intersection, we can write it like this as well. For any epsilon, there is an n such that after that n, a infinity is in this ball. It's logically equivalent, these two things. Okay, fix an epsilon. The sequence of sets is Cauchy, which means that there is an n capital such that after that, so if lowercase n is after or larger than uppercase n, and for any p, the Pompeiu-Hausdorff distance between these two guys is bounded by epsilon. Now, one of the exercises from last week says that this in particular implies that this term is in the epsilon ball of this and vice versa. I'm going to use this really. Okay? So in the statement that I'm trying to prove, I took an arbitrary epsilon. There exists an n, is this n is this n. Okay? So this is the n in the statement. To be proven. So what do I need to do? I need to fix a lowercase n after this uppercase n, and I need to show this inclusion. Fix want. Maybe I should write it here. Once, if I can show this, I'm done. Okay, so you take a point here, and you show that it's here. Okay, that's how you show that one set is included in the other one. Well, I guess one thing that is important here is this, right? So what I'm going to do is I'm going to take a point here, which means a bunch of things, but ultimately I'm going to show that it's included in this ball. Now the statement says that I have already fixed that n, which means that I cannot change that n after taking my points. Okay? So that capital N has to work for every single point in this A infinity. Okay? I am basically following Barnsley's proof, but the way he's writing it, he makes it sound like he's changing n based on the point. So, okay, let x infinity in A infinity. So maybe I should write it here. This is what I want now. I want this point to be inside this ball. Okay? Because x infinity is in A infinity, I have that there's a sequence that I obtain by sampling this A bullet sequence that converges to x infinity. Okay? Okay. Now, lowercase n is fixed, okay? That's a fixed number now. I cannot change that n. And probably it's not good to use it as a dummy variable. It's not a dummy variable at this point. I used it. So let's use m. So for any epsilon, there's a capital M such that for any lowercase m larger than uppercase m, the distance between these two is, let's say, bounded by 1. But in fact, let me do this. Oh, okay, let's do it like that. I don't want to do that. Let's do this. consider I'm going to consider a certain subsequence of x bullet defined by saying that the mth term of the subsequence is the mth term of the sequence plus n is that number. So I have the sequence that converges, and I can certainly take a subsequence of it by saying, let me disregard the first n terms. Okay? That still converges to the same point. Because I just got rid of the first parts. The tail of a subsequence chosen like this has to be the same. But further, note that this guy, which is x sub n plus m, which by definition is a sub n plus m, which is something like this, which means that that set is included here and is still fixed. Okay? So x prime bullet is a sequence that converges to x infinity, but it is also in this set. Now, here's an exercise for you. This set is closed. Okay? Let me just write it like this. Okay, so if I have a set that is closed, a sequence in it that converges to some point, well, that limit has to be inside as well. Which is what I wanted to do. And what is the exercise? The exercise can be written like this. If I have a compact non-empty subset and an arbitrary radius, then this open ball centered at A is open in X, and the closed ball is closed in X. This exercise is this exercise. Okay? Questions about this? Okay, 3, proposition C, I guess at this point, that if I have a Cauchy sequence in the hyperspace, its inner pk limit is totally bounded. So I feel like going this way, we're going to have metric spaces 4. So we're going to have a whole month for metric spaces. Because there's still things to be proven. Okay. Is a Cauchy sequence in the hyperspace, then A infinity, which is this pk inner limit, is totally bounded. Proof. Now I'm going to use proposition B, which gives me sort of like this epsilon delta thing that we just proved. Um, we just proved this. I'm going to need only the nth term, the capital nth term. And of course, if I lift this intersection, it's going to grow possibly. So I have this. Okay. If A infinity, the pk limits, were not bounded, not totally bounded, that would mean that there is some epsilon 0 and a sequence in A infinity such that the distances between any two terms in the sequence is bounded from below by epsilon 0. Okay, now here let's choose epsilon to be, let's say, epsilon 0 over 10. Okay. Now, this sequence is in the limit set by the proposition, as I wrote. It's included here. Okay. Okay. So that means that for any term here, there is a point here that is not more than epsilon 0 over 10 distant from this. So for any n, there is a y sub n and a sub capital N such that the distance between these two is bounded by this. Any ideas as to how this continues?
Something with the triangular inequality?
Ultimately, yes. So, look, this capital N is fixed. Lowercase n is not fixed. Okay, they are irrelevant, irrelated, not related to each other. But what is the case here is that y bullet is a sequence here. Okay, I'm not going to write the rest of the proof. I'm just going to say it out loud. I have a sequence in this set. And this is a nice sequence. It is related to x, to the original sequence, like this. Somehow, y bullet tracks the x bullet sequence. Now, this is a sequence in a compact set, which means that there's a subsequence that converges to some point to this. Okay? Okay, I'm not going to write it. I am going to write it. I use the compactness of A sub n. And then, using the same indices here, I have a corresponding subsequence of x bullet. Okay? I'm sampling the terms that I sampled to get this y prime here. Okay? this lower bound applies for any two terms. In particular, it applies to these guys. Put in the tracing terms. Okay, this is bounded by epsilon 0 over 10, and so is this, which means that this is bounded by epsilon 0 over 5. Plus this term. Okay, but y prime is a convergence sequence, which means that it's in particular Cauchy, which means that I can bound this by some number that would give me a contradiction. Let's say by 5 for large enough and m, which means that this will be bounded by, what is it, 2 epsilon 0 over 5, but there's no way this is strictly larger than this, right? Because epsilon 0 is a positive number, which means that that's a contradiction. Which means that indeed A infinity has to be totally bounded. I haven't made any mistakes, hopefully, in the middle somewhere, which means that I started with something wrong. Questions? And this is a long proof. I thought we would be done with this whole thing, but and it's like a basic, technical thing that we're never going to worry about anyway. But we started doing it, so we're going to finish it. It might be good to sort of like try to reconstruct these proofs with your own notation and stuff like that, and draw pictures as to what is happening. Okay, so we have a bunch of things. We have like basically half of the theorem that completeness is inherited. Let me just see if I'm missing anything. I'm not missing anything. Okay, so now I can state the theorem. We had proved one side of it, and so all this business is to prove the other side. And we still won't be able to finish it because I have like 5 minutes left. But we're almost there. Okay? So these were the subquests, and there are 2 more subquests, and then after that, the whole thing is done, and we're going to get the achievement points. Okay. But note that so far I haven't used anything about the completeness of X. I took compact non-empty sets, took sequences of such sets that are Cauchy, and I was able to say certain things about this limit in this other sense, this Painleve-Kuratowski sense. Now it's going to turn out that, if you have a complete metric space, and if you take a Cauchy sequence in the hyperspace of it, the Pompeiu-Hausdorff limit is going to coincide with this limit that we were looking into. Then X is complete if and only if H of X is complete. On Canvas, under resources, there's a set of lecture notes that I put. It's by Sternberg. He's like one of the main guys, one of the big guys in dynamics. And he has sort of like this lecture notes on dynamical systems. And at some point, he is sort of talking about these kind of things. But for this particular theorem, he says, oh, it's basically technical. This is the idea. So he doesn't go into the details. But and I was like, when I looked at that, I said to myself, I will prove it. And now I know why he didn't prove it. OK. We did the backwards direction last time. So if h of x is complete, we show that x is complete. Now, the claim is going to be, OK, let a bullet be a Cauchy sequence in h of x. I'm assuming that x is complete now. And I took a Cauchy sequence in the hyperspace. In order for h of x to be complete, I need to be able to show that this indeed has a limit. And the limit is going to be the limit that we were looking into. This, the pk limit, inner limit, is inside h of x. And let's write it like this. Limit as n goes to infinity of the distance between the nth term and a infinity is 0. So that an converges to a infinity in the sense of Pompeiu-Hausdorff. In this sense that we were looking into. Two things. Now, by the propositions that we proved, let me just write down what we have so far about this limit. Well, I think not all is lost. Just like these are basic arguments that I think is useful that you've encountered already have. We showed both of these in different statements, in different propositions. But you see, A infinity is a subset that is closed and totally bounded of a complete metric space, which at this point we can say that A infinity is compact. So it's a compact subset. And yet, we don't know if A infinity is non-empty. Okay, we still don't have it. So we still don't know if it's here, but at least it's compact. And we also have this. Now this looks bizarre perhaps, but it turns out that this is one half of this statement. Recall that, one sort of definition for this is this is included in a bowl of this, and this is included in a bowl of this. So this really is about this is included in a bowl of this. So we're going to have to prove the other way around. So we have two things to do. Show that this A infinity is non-empty, and the other way around intersection relationship also holds. So two things to prove. Which we're going to do next time. Okay, thank you. I'll see you on Thursday. Okay, let's start. Good afternoon. So today, finally, we're going to finish this proof of this technical theorem that completeness is inherited by hyperspaces. And then hopefully we're going to start talking about dynamics a little bit, where things get a little bit more fluid, let's say. So far I was just focusing more on sort of like these technicalities and formality and stuff like that because I think it's somewhat useful. But when you switch over to dynamics, it's not a fundamental field necessarily, at least the way we're doing it now. And all of these stuff, you just say it's obviously true, or it's a technicality, or someone else probably did it before, or something like that. And that's not your main problem usually. Okay, so let me remind you what we have. I take an arbitrary metric space X, and we have a bunch of propositions and lemmas. Extension lemma was about this, being able to take a sequence of points from a subsequence of sets that is Cauchy, and then you get extended. First proposition is that if you have a Cauchy sequence of compact non-empty subsets, then this inner pk limit, a infinity, is closed. And recall that this is the definition. I didn't finish writing the set, of course. So what should be the limit of a sequence of sets? Well, it should be the set of all limits. That's the point. You sample one point from each of these sets, and you look at where you can converge. And so we show that that is closed. And as an exercise, really, you don't need to assume this. If you were to take any sequence of subsets, maybe closed, maybe not compact, whatever, and it doesn't need to be Cauchy, this inner limit set still makes sense, and it's still a closed set. The proof that we used doesn't really apply to show this, but this is still true. In the notes, I wrote a couple of different ways of writing this inner limit, and if you use one of the characterizations, it becomes rather straightforward to show this, but it's an exercise. Second proposition is that if I have a Cauchy sequence again, then I have this inclusion statement for any epsilon. There's some time n after, such that if I wait n time, then this limit set is going to be in the epsilon ball for any element in the set, in the sequence. Third proposition, if I have again a Cauchy sequence, then this limit set is totally bounded. Okay, these we proved. And the theorem that we have, that we want to prove, is this. If I have a metric space, then X is complete if and only if h of x is complete. And furthermore, if I have a sequence of sets in h of x that converges to something, A bullet converges to B, then B has to be this set, okay? So if you have sort of like a convergent sequence of sets in h of x, you know what that limit should be as well. It is given by this. And we did the backwards direction last week. If h of x is complete, then x is complete. We did that. So the forward direction. So I need to show that h of x is complete, which means that I need to take a Cauchy sequence of subsets, and I need to show that it has a limit. Okay. So the first claim is going to be this: A infinity is inside a hyperspace, so that's an admissible target. And second of all, indeed the sequence converges to this A infinity. Okay. Now, here are some reductions. We have done a bunch of work already so far. So that's going to come in handy. I take a Cauchy sequence. Then by proposition A and proposition C, A infinity is both closed and totally bounded, which means that by the factorization theorem, it's a compact subset. Maybe I should write it. But we don't know still that A infinity is non-empty. Recall that one of the conditions for a set to be in h of x is that it is non-empty. So still we need to show. So need that's the first thing we need. And then the second, let's say that we have this. The second thing is that we need this convergence. And here's an exercise. This is just basically a logical exercise. It says that if you have a convergence, a sequence of sets converging to some other point, some other set, then we have for any epsilon there is an n such that the limit, I guess this should be B, Red. Then the limit should be included in this intersection, and vice versa. The union of the tails should be included in the epsilon ball of P. Now you see, by proposition B over here, we already have this part. We don't have this part though. So we have this as well. Oh. Which means that we need to show this. For any epsilon, there's an n such that the union of all the sets after uppercase n is included in the epsilon ball of A infinity. So I need. So. Okay. Any questions so far? Let's first do this. So here is where I'm going to use the extension lemma again. So what do I need to do? I need to be able to produce a limit point like this. I need to be able to say that, oh, I can take a sequence, I can construct a sequence in X such that each term is coming from one set in the sequence of sets, such that that sequence does converge to something. Okay, claim. I'm going to look at my notes. I don't remember. Okay. So the only thing I have is that A bullet is Cauchy. Okay, which means that, you know, for any epsilon there's an n, blah blah blah. Now I'm going to use different epsilons, and in fact I'm going to use epsilons of the form 1 over 2 to the k. So for any k, I'm going to be able to do something. So let me write it. For any integer, positive integer k, there is some n sub k, that depends on k, which I want to be less than or greater than n sub k minus 1, and so on. This is like an induction thing, if you want. Such that for any n after n sub k, and for any p arbitrary, I have that the Pompeiu-Hausdorff distance between a sub n and a sub n plus p is bounded by 1 over 2 to the k. Okay. Are we all clear that I can do this? This is like a logical trick that I'm doing here, but if you're not used to these kind of things, it might be confusing.
That's word my thing, because I remember we talked about last time. I thought it was interesting how we're able to choose this 1 over 2k because it still applies to this epsilon argument because we're choosing every epsilon. Not
yes.
Okay.
Yeah, for any epsilon, there's an n such that blah, blah, blah happens, right?
So
but yeah, so, but I'm not saying there's a unique n. So I can take this capital N as large as I want. I can just get rid of the first however many terms I want. And so that's how I can construct this. So for instance, what does this mean? This means that if k equals 1, so I chose k equals 1, my epsilon is 1 over 2. I'm saying there is some n sub 1 such that after n sub 1, this happens. Then I say, okay, I want better estimates. Let's choose k equals 2. Then there's some n sub 2 that is larger than n sub 1, the previous time that I had chosen, such that after n sub 2, the bound is 1 over 2 to the 1 over 4, and so on. You keep iterating like this, and this gives you a sequence of times, basically. Okay, so put A prime sub k to be the associated subsequence. Okay, so A prime now is a subsequence of A. You see, I'm trying to use this extension lemma. What I did was, initially, the only thing I knew about A was, the A bullet, the original sequence, was that it was Cauchy. Then I switched over to a subsequence to get explicit bounds. Okay, so now I get to choose some points. So pick x1 prime in the first term of the sequence. Okay. So now I wanna have a point in the second term. So A sub 2 prime, that is to say A sub n sub 2, right? So I want to pick a point like this. But you see, n sub 2 is after n sub 1. So if n lowercase n is n sub 1, n sub 2 is of the form n plus p for some p, which means that the Pompeiu-Hausdorff distance between the first term of the subsequence and the second term of the subsequence is bounded by 1 over 2. Okay? In particular, recall that this is dominated by sort of these set to point distances and blah, 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 which means that there's a point here that is at most 1 over 2 distant to this point. Any questions about this? Now I keep going. Erase this now. Well, again, in this expression, if I were to choose lowercase n to be n sub 2, then n sub 3 is some number larger than n sub 2, which means that it is of the form n plus p, which means, by the same reasoning, so now this, such that this is bounded by the Pompeiu-Hausdorff distance between A sub 2 prime and A sub 3 prime, which is bounded by 1 over 2 to the 2. And you keep going like this. Okay, so and I'm only comparing the distance of the kth term to the k minus first term. Should be minus 1. Okay, so this gives me a sequence of points that I sample from the subsequence of sets. The claim is that this sequence is Cauchy. Okay, so how do I show this? Well, I need to compare x sub k plus q, let's say, or x sub k prime to x sub k plus q prime. Well, how can I bound this? Well, I can just put the middle terms in there, right? I can apply the triangular inequality as many times as I want. Okay, so the bound grows, of course, but as you're going to see, I chose these 1 over k's in such a way that this, or 1 over 2 to the k's, in such a way that this sum is going to converge, that it's going to be something that I can bind. And then x sub, so the final one is k plus q minus 1 prime x sub k plus q prime. Okay, this is bounded by 1 over 2 to the k, and then 1 over 2 to the k plus 1, and then all the way up to 1 over 2 to the k plus q minus 1. Okay, let's factor out 1 over 2 to the k from this. So that I have 1 plus 1 over 2 plus dot 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 plus 1 over 2 to the q minus 1. So this guarantees that this is a Cauchy sequence. I'm not going to finish writing this. I think this is a good exercise for you to finish. But what is the idea here? I need to be able to bound this distance by something that possibly depends on k, that decays with k, but that does not depend on q. That's what it means for a sequence to be Cauchy in a sense. And so you see, this is a geometric, or this is the first part of the geometric sequence, a series. So let me just say, then so that's an exercise that this really gives you that this sequence is Cauchy. And here you need to use this idea that if you have this, there's a closed form for this. Do any of you know this? The sum of a bunch of terms, but it's like powers of some number.
I knew it at one point, but I do not remember at the moment.
Okay, I keep forgetting too, but at least you need to be able to know how to derive it.
Right.
So q minus 1. Okay, so r is some number here. So if I were to multiply this by 1 minus r, what do I get? I have this telescoping thing, so I get this whole thing. And then minus r squared and so on. So r to the q minus 1, and then at the end I'm going to have a minus r to the q, which means that this is 1 minus r to the q. Okay. If you've taken linear algebra from me last semester, we used the same thing when we were proving the ergodic theorem. So that means that if I were to take this to the other side, then that sum is this 1 minus r to the q divided by 1 minus r. Okay, now if r is less than 1, and if I take q to infinity to get the series, this is going to decay to 0. So that the geometric series is going to give you 1 over 1 minus r. In this case, r is 1 over 2. So it's a finite number. But then, so this is bounded by some number that is finite. You can literally compute what that is. I guess, I don't know, plug in. And then here's a term that decays by k. So that is Cauchy. Okay, that's how we do it. This is a very good trick. Any questions about this?
I was going to explain, or not explain.
Yes.
It may be, is it sort of a similar same logic we used earlier for saying how this is Cauchy with 1 over 2k and relating it back to epsilon?
Yes.
Okay.
Now, okay, so that's the point, right? So initially when I started with Cauchy, I had like for any epsilon whatsoever. And using that, I could have sort of, let's say, farmed that epsilon to get some explicit bound. If I wanted, I could have said 1 over k here as well. But then if I do 1 over k, this argument doesn't work because the sum of 1 over k's diverge. So I want something that converges if I add. if I wanted, I could have done like 1 over, I could have chosen something that converges even faster than this. I could have chosen some, hyper exponential function or something. But this works, and it's easier to compute the geometric series and so on. So, any questions about this so far?
So, if you were like coming up with this proof,
Yes.
and so like when you pick 1 over 2 to the k that you're ending up with something like this.
Yes.
That's why you picked it. So, is it just kind of like where you're ending up? So
Yes.
That's why.
Yeah. Yeah, because like ultimately you want to get a Cauchy sequence. And this is like one of the standard tricks of proving something is Cauchy. Because like you have the kth term and then k plus qth term, and q is arbitrary. So these 2 times could be arbitrarily distant from each other. And so how can you bind this? I mean, there are other tricks too, but like this is the most standard trick probably. You just put the middle terms in there. Yeah. Okay, so we have a Cauchy sequence sampled from a subsequence of the sequence of sets A, bullets. The extension, we can do it a couple of ways. Let's say the extension lemma says that you can extend this to a Cauchy sequence. X is complete. That was an assumption, which means that it converges, whatever that sequence is. Okay, so that's the end. So there's a Cauchy sequence in this. That is a supersequence of x prime bullet. X is complete, which means that it converges to something. By definition, whatever that converges, whatever this sequence converges to, has to be in A infinity. Let me not write it. I don't have space. Okay. So we showed that this limit set is indeed non-empty. It has at least 1 point in it. And it might be the case that it has only 1 point. Okay. Okay. That was the first part. And then the second part is this inclusion business. And so you see at this point, we have that A infinity is a point in the hyperspace h of x. It was compact already, and we showed that it's non-empty, which means that it's a point in the hyperspace. The second claim, which is this other half of Pompeiu-Hausdorff convergence, which is this. For any epsilon, there's an n such that if I were to take the union of all of the tail of the sequence of sets, then it's inside inside the epsilon ball around A infinity. Okay. By the way, I realized an ambiguity here. When I'm writing this, I really mean this in the sense of a subset of this x. So I'm saying it's a set of all those points that are not more than epsilon away from some point in A infinity. But you could also interpret this as the epsilon ball in the hyperspace. Right? These are different things. These are not the same thing. I don't mean this, I mean this. Okay. So this would be the set of all those compact non-empty subsets of x that is not more than epsilon far compared far from A infinity using the Pompeiu-Hausdorff distance. That's a different thing. The types of objects are different. Anyway, so I mean this. Okay, so let epsilon be positive. Now I'm going to do something very similar. Again, I'm going to use the fact that a bullet is Cauchy. For any k integer, there is some number n sub k that I might as well choose to be increasing in k. Such that for any n after n sub k, and for any p, I have that the Pompeiu-Hausdorff distance between a sub n and a sub n plus p is bounded by epsilon over 2 to the k. Epsilon is fixed after all. You can just use it as a number, and this is a valid upper bound. I can do this. Okay. So this epsilon is going to be this epsilon. Now, I need a capital N. Let me let this n sub 1 to be that capital N. So this n in the statement is the first n that I chose in this farming bounds business. So now what do I need to do? I need to take an arbitrary n larger than uppercase n, which is n plus 1, n sub 1, and I need to show that that set is included here. Now, the moment you see something like this, you should again expect that I'm going to sort of do a similar trick. I'm going to have sort of like a chain of points, and I'm going to sort of add the distances between them to get an upper bound. So claim. I fixed my capital N, that's the n I claim, and I fixed my lowercase n. So I don't get to move any of these terms anymore. Okay, so let x be in a sub n. I need to find a point in a infinity that is not more than epsilon distant from x. Okay, how do I find a point in a infinity? I need to be able to construct a sequence of points using by sampling points from this sequence of sets. Okay, so let's write it like this. I think this is going to be the nice notation. A0 prime is going to be x. Okay, we go back to this. Lowercase n is after uppercase n. Uppercase n is n sub 1. Okay, which means that if I choose, okay, now things are getting perhaps complicated, but so if this were n sub 1, lowercase n would be this, which means that x0 prime, x1 prime is bounded by epsilon over 2. Yes. Questions about this? I keep sort of like changing the indices 15 times, but so you see, that's why I put bullets if I don't have dummy variables, it's not confusing. But this n is dummy here, okay? And p is dummy as well. So let's just look at this. I'm just using the first guy. For any lowercase n after n sub 1, okay? So I can choose lowercase n to be n sub 1. And this n, it's a number after this, which means that it is of the form n plus p, where lowercase n is uppercase n minus n sub 1. So maybe I should write it like this. Green n goes here. Okay. And because this index is 1, k equals 1 here, I have this bound, epsilon over 2. Okay. It really isn't that deep of an idea. It's just index management. It does get complicated or confusing a little bit though. Okay, so I have this. And how did I get this? I did this minimax blah, 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 and I realized that this is bounded by the Pompeiu-Hausdorff distance between this set and this set. That's how I got this. And then I can keep going. D from x1 prime to x2 prime is bounded again. It's the same bound after all, epsilon over 2 again. But then, if I keep going, two against 3. Now my bound starts decreasing. Okay, maybe I should write it like this. So to get x sub 1, I used n against this, n sub 1. To get this, I used the fact that n sub 2 is after n sub 1. So this is k equals 1. This is again k equals 1 in the expression over there. And here I compared 2 to 3. To get this, I compared n sub 2 to n sub 3. So with k equals 2. And I keep going like this. Okay? So this way, I have a sequence. Let me write it over here. Oh, yes.
So I was going to ask, we're fixing n. However, there seems to be this whole prospect here of these distances are still decreasing and decreasing.
Yes.
Wasn't n only just greater than capital N sub 1?
Yes.
So how are we getting to this point here of...
Well, I used, so this was the n that I had fixed.
Yes.
And then I farmed the epsilon delta business to get this expression.
Okay.
Okay. Now, I'm not using lowercase n anymore.
Okay.
Now I'm going to compare some other point to this point that I chose.
Mm-hmm.
And I'm going to keep going like this.
Interesting. Okay.
Yes. I mean, admittedly, this is not the most formal way of doing this. Like, you should be able to sort of tell this to a computer to do, but things do get complicated. But like, if you want to sort of make things more formal, you need to be more explicit about this index management, which, you know, is useful sometimes. But I don't think it becomes harder to explain, perhaps, to do that index management. Okay, so we have then there is Okay, so there is a sequence of points that I chose from this subsequence. Okay, and again I do the same thing. I'm going to compare the k term to k plus q term. And I'm going to do the same thing. Oh, -1 prime. Okay, now you have two cases if you want to be technical about it. Either k is 0, in which case you have this plus epsilon over 2, or k is not 0, in which case you have this very nice geometric thing. What is the point is that this is bounded by some number, by epsilon, and then some number that doesn't depend on anything, divided by 2 to the k, and that's it. Okay. Just like do the same argument that I wrote before, that I left you to do. You do it again, and you get this. So C doesn't depend on anything. K, Q, epsilon, and it doesn't depend on anything. Okay? Okay. What is more is that okay, good, okay. So this shows that it is Cauchy. I obtained it by taking points from a subsequence of sets. By the extension lemma, I can extend that sequence. Okay, because X is complete, it converges to something. Same ideas. There's this. That is a supersequence, and it converges to some point x infinity, which by definition is in the limit set. Well, if this guy, the supersequence, converges to this x infinity, certainly any subsequence of it too converges to the same point. I mean, it's Cauchy. I could have said it converges too, but okay. Well, and in fact, any point is, okay, there you go. So in this expression, if I were to choose k equals 0, I would get that, and k equals 0 and take q to infinity. This goes to x infinity. This is just the original point that I had chosen, this point. Maybe I should write it. Gives that this is bounded by epsilon over 2 or something. It's bounded by some number, but in any event, I was able to find, given x, the original point that I had chosen here, I was able to find a point here that is not more than epsilon away from the original point. Okay, and so this is the end. Questions about this? This is essentially the proof that Barnsley used, Barnsley gives. There are a couple different proofs using some of the other definitions of Pompeiu-Hausdorff distance and everything, but this is one way. And if there's some confusion, we can again talk about it and perhaps we can sort of discuss what are easier ways of proving this whole thing. So ultimately, I was able to show that that is there, which means that I was able to show that inclusion relation for any epsilon there's an n such that the union of all the tail after n is included in the epsilon ball of the limit set, which is the other half of the Pompeiu-Hausdorff convergence that we were missing, which consequently means that it is indeed convergent. So from here, maybe I should put here. And that's the end. I started with the Cauchy sequence in h of x. I had this set. I showed that it's a point that is admissible as a limit. It's an h of x. And I showed that it's, this limit does converge. And so that means that h of x is complete. And this is the end of the proof. And the proof is complete. Okay. Let's take a 5-minute break. And then when we come back, we're going to switch over to dynamics. Question? Yes. Okay, welcome back. So we're done with the first part of the class, which was rather more technical and more abstract, this background stuff. And now we're really sort of switching over to dynamics and fractals and how they're related and so on. And probably at this stage, you're basically on your own. You get to sort of like the whole world opens up, basically, whole world of dynamics, and you get to study whatever you want at this point. I'm expecting more and more divergence as to what you guys are looking into on an individual basis from now on. And since we've been doing so much technical stuff, I thought the rest of today we can just look at some of the examples that are related to dynamics and fractals and stuff. And so I wrote some of the examples that are sort of from all over the place, all over math. And so I thought maybe we can decide on some of them and start talking about some of these examples. Okay. Any requests?
I've heard of the horseshoe before, but I don't remember what it is in these slides.
Okay. So we start with the Smale horseshoe. I'm gonna just draw pictures often today. Okay, I'm not gonna for the rest of today. So let's start with this. So this is one of the paradigmatic examples of what is called stretch and fold dynamics. So part of this hyperbolic theory, or stretch and fold dynamics theory, and perhaps I should say, even before going into this, there's this example, okay? Candy making. You have like this hot candy, and then people sort of like pour it on something and stuff, and like there's like some coloring, but then sometimes they want to sort of satinize the candy. They don't want it translucent. So often in these candy making places, there's like a hook, large hook attached to the wall, something like this. And so one of the guys just takes this and sort of like starts hooking it. On YouTube, there's a bunch of videos of this. Imagine it's like a dough, and you sort of it's hot and it's like melting and stuff like that. You just like hook it, and you keep hooking it. Okay. The point is that you keep folding, and the point of doing this for the candy maker is that they get to sort of, in a very homogeneous manner, they get to fold in little air bubbles, which makes the candy satin, like opaque. The idea being that this stretch and fold type of behavior somehow mixes things very good. And this is an obvious thing, perhaps. It's an obvious thing, perhaps, for someone who's spending a lot of time in the kitchen or something. But it's also true in dynamics in more abstract setting. And the horseshoe is an example of this. So you start like this. And Smale was trying to understand, Smale is a Fields medalist from a while ago, who also happens to be an academic advisor, academic ancestor to me, but anyway. So you start with a filled-in square. I'm not going to fill it in, but it's a rectangle. So what you want to do is you want to stretch and fold. So imagine you're pulling it like this. So maybe I should draw it like this. This was the original place. And now you stretched it. And now you have something like this. I'm going to draw better. And these sides should be so that the area of this is the same as the area of this, so that you're not sort of missing any material. This is not the first iteration of what is going to happen. Then you fold this piece into the original space that you started with, so that now you have a shape like this. And this is why this is called the horseshoe. Okay? So this, from going from here to there, is one step, really. I drew this, the middle step to be more explicit. Now you keep doing this, okay? You say, okay, let me get rid of these pieces and apply the same reasoning to this piece. So I started with this candy, and I'm sort of starting to hook the candy. This is where the hook goes, if you want. Now, to say anything about these from a mathematical point of view, you're going to have to use like numbers and stuff like that. But let's at first understand the idea. So this is just one step. One iteration, let me say. Now, if I were to do the same thing to what is still inside the original area, well, this is going to stretch. So inside this, I'm going to have two smaller strips, okay? One coming from here, the other coming from there. And then when I fold it, I'm going to have two of these. And I'm going to have two strips inside each of these. So I'm going to have, if this was the previous area, now I'm going to have, oh, that's a bad color. I'm going to have even smaller strips here. And then I keep going. The next stage, the green areas are going to have even smaller strips inside them, and so on. Now, as you can see, ultimately, you get something that is pretty much like a Cantor set. Like it's Cantor on this side, and it's like a bunch of like lines on this side. So Cantor, let's say horizontally. Any questions so far about this? Now you see this is a very dynamical process, and we can make this like more natural. You can sort of embed it into sort of like smooth manifolds or whatever, and make it like more natural. But this is sort of like the bare bones of the example. So somehow you have this dynamical example, something just like evolves in time, and ultimately you end up with something that is related to a fractal. And of course, how can I talk about this end result, this residue, this attractor, from a dynamical point of view. Maybe this is not that straightforward to see, but we're going to spend a lot of time on this idea that whatever is left is in fact invariant under this procedure. Because if you go to the end of time and you have this Cantor set, well, if you keep doing this, you're going to end up at the same place. I mean, maybe your point is going to move, but the set itself is not going to move. So that's going to be an invariant set. Yes?
Just kind of like a general question. Are we like the space where we're talking like just a general metric space?
In this case, it's an open ball in R2 in the plane.
Okay. Can you like
yes.
generalize it?
Yes. I mean, this folding could be sort of like this way or this way, whatever. Yes. And there are like more general ideas based on this. These are things like blenders and blah, blah, blah. People go crazy, as you can imagine. Yeah. Any other questions about this?
So we just ignore the stuff out of the square? Like this horseshoe?
Yeah. You don't actually have to ignore. You can say, yeah. But of course, I mean, there are a couple different versions. It's like if instead of doing it like this, you can do like this if you want. There's like 50 billion different versions of this. But of course, you can go backwards as well. If I were to go backwards, so I'm trying to think, what is the transformation that goes from here to there and from here to there? Well, if I'm going this way, I need to stretch this way and fold this way. Okay? So if I need to go back, I need to stretch this way and go that way. Okay? If you go that way, and if you start with this, what you end up having is basically the same thing. It's a Cantor set, but instead of having horizontal Cantor, you have vertical Cantor. And if you wanted a subset of the rectangle that is invariant both in forward time, going that way, and in backward time that way, what you would need to do is to take this and intersect it with this, which again is yet another Cantor set. It's a different type of fractal. So you would have the intersection of both of these would be Cantor horizontally and Cantor vertically. It would be, I guess, Cantor dust, if you want to call it something. Okay. So that's one example. Any questions about this? So for the rest of the day, we're just trying to open up the horizon.
Okay, general question, a little
Yes.
bit less about specific mathematical things, but maybe
Yes.
more about how this applies to future weekly reports and whatnot. Is
Uh-huh.
your expectation more or less looking into one of these and then building up a variety of prerequisite ideas into it? Or do you think we have most of what's needed for most of these dynamics?
Yeah, it could be that. For instance, one thing that you can immediately answer about this is that if you're careful about this, this Cantor set or this Cantor set or their intersection is going to have Lebesgue measure 0. Okay. Then there's a paper that I've uploaded on the under the resources page. It's by someone called Bowen, and he was able to come up with just the right numbers so that ultimately this attractor that you get, the attractor for the horseshoe, has positive measure. So that could be something that you study for the final project. So that could be one way in which you interact with these things. Or you keep reading the Barnsley book. Some of these examples are from there. Things like this. So it's just that, yeah. Is this answering your question?
I think so, yeah.
Yeah. Initially, I was thinking of sort of, talking about dynamics from an abstract point of view, group actions and blah, blah, blah. But since we've been doing so abstract stuff, I decided let's just focus on specific examples. And I just wanted to also show the breadth of dynamics in a sense. There are certain applied items and so some more, like formal items and stuff like that. And dynamics is all over math. And depending on what you want to do, what you want to look into, you have a bunch of different options. That's what I'm trying to sort of exemplify. And these are the examples that I'm comfortable somewhat to sort of discuss. There are more examples that I know, but I'm not very comfortable discussing them. I don't know them very well. I mean, I don't know these very well either, but I know these better than the other ones that I don't talk about. Anyway, yes?
I'm interested in what the Peano axioms
Peano, yes.
have to do with dynamics.
Yeah, so this Peano axioms is about like building basically numbers and arithmetic and stuff like that. I'm going to be sort of a pedestrian about this because my foundations isn't that strong, but the point is that you want to sort of like come up with certain axioms that allow you to do arithmetic and basic and all that stuff. Now, from a dynamical point of view, or if you have sort of like the eye for this dynamical ideas, one of the big things, one of the big part of this Peano axioms is that you're assuming that there's a certain dynamical system. And that is this dynamical system given by the successor function. I don't have much to say about this, but let me just say that this needs a dynamical system. By need, I mean you're assuming when you're trying to build these things. Successor, which means that you say, okay, there is something, there's a number, and there's something called a successor dynamical system. And given any number, its successor is not itself. Okay, so there is something, there is a dynamical system S, and S of x is also something, but it's not the same thing as x. And then you keep iterating, and that gives you the integers and whatever, all that stuff. Okay. Was this satisfactory? I don't have anything too deep about this to say, but I bet there's a bunch of stuff.
And when we use like just the word dynamical system in this, are we just kind of trying to like solidify the idea that like the successor function moves something a certain amount consistently?
Yes.
Okay, so
Yes.
that's the core idea of that.
Yeah, I mean,
you can say this is a dynamical system because this moves something
exactly.
consistently.
Yeah, I have this guy, and it goes somewhere else, and it goes somewhere else. And if I were to say, okay, there's a successor function such that after, I guess, 5 iterations, even though I don't know what 5 means, it's like if after 5 iterations I get back, that still gives you a number system. It's the modular arithmetic after all. But it's not the integers. You get something else. The idea is still dynamical. You get something else, though. Okay? Yes?
About the sawtooth map.
Okay. This is also something related to these stretch and fold business. But it's much simpler than the horseshoe. This is also called the expanding map. And there are a couple of ways of looking at this. But because I called it the sawtooth map, let's just use the notation that is appropriate to that. And as you see, while I'm sort of like trying to impress you guys a little bit and like influence you, at the same time, dynamics is a new field in a sense, and like a big part of dynamics is to really understand certain examples, okay? Because many of these examples, I mean, some of them are more specific, but they sort of like, they are like paradigmatic. Once you understand those examples, it sort of like opens up sort of certain ideas. And so this is a function, maybe I should write it like that, defined on the interval. And it is defined, I can write it in 2 ways. Let's write it like this. F of x equals 2x mod 1. This is one way of writing it, or you can write it in a piecewise manner. So this is 2x if x is between 0 and 1 over 2, and 2x minus 1 otherwise. And how does it look? Well, I can just draw the graph of it. That's my unit square. That's the main diagonal. It looks like this. That's how f looks like. Takes 1 over 2. And here, from 0 to 1 over 2, it is linear after all. It stretches by a factor of 2. You see, it again stretches. Now, there's discontinuity here. It's not a continuous function after all, but it is piecewise continuous. And it has only one discontinuity. Yeah, let me say this too. If you want, you can also. So, does anyone understand what I mean by this mod 1? I have sort of like a fractional number, perhaps. Okay, you're saying no. So, if I were to look at f of 3 over 4. So now it becomes 3 over 2 mod 1. I just use this formula. But mod 1 means, so this is like a fractional number, get rid of anything left to the point. So this is now 0.5. So this is 1 plus 1 over 2, get rid of the 1, because I want to get back into the interval. So that I can keep iterating. Okay. Another way of writing this would be to sort of think of the same function, not necessarily on the interval, but on the circle. So you can say t for one-dimensional torus if you want, 0 to 1, mod 1. So what does this mean? I'm saying the interval, but 0 has to be the same thing as 1. Okay, so that means it's a circle. Well, if you think of it like that, this just becomes multiplication by 2. You stretch the circle by a factor of 2 and put it back in. Okay. Now, you can do the same thing using complex numbers. In fact, one of your reports is basically about this. You can also think of it like this. Call S1 to be the complex numbers whose modulus is 1. So the unit sphere centered at the origin, well, you can think of this as z squared. These are all the same thing. Now, what exactly does the same mean? Obviously, they are not exactly the same, but they are what we're going to call conjugate. So we're going to develop this idea of conjugacy. It's basically sort of a way to change coordinates of your dynamical system, or like where the dynamical system acts, in such a way that you get a different representation of the same behavior. We'll discuss that more in detail. In Barnsley, he's using the word address. Yeah, so this is also something that you keep iterating. So there's a famous example, which is this game of life, but I don't quite remember the rules of it. I'm just going to give you a simpler example. Many of these examples you can find in Schroeder's book as well. He goes into sort of like intuition and why people are looking into this and everything. So these were first considered by Ulam and von Neumann, as far as most people are concerned. Of course, von Neumann is involved in this, and this is sort of related to, you know, like the architecture of computers and all that stuff. And when people were trying to understand these things for the first time, this was like a toy model. And then later on, I guess back in the 80s, Stephen Wolfram of Wolfram Alpha fame now, he sort of got into these things. And so you start with a ticker tape. And this is your world. You can have higher dimensional ticker tapes as well, but the example that I'm gonna give is one-dimensional. And time is gonna go that way. The point of a cellular automaton is that, maybe I should draw a couple more. Is to start with a bunch of things in each of these. It could be, let's say, 0 or 1 values. It could be some other things. But the point is that if you want to figure out what should happen here, all you need to do is to look at some neighborhood of the same space in the previous state. It doesn't depend on, it depends on one rule that is local. That's the point. Which means that, so this is a significance perhaps from a scientific point of view of these objects, which means that if perhaps you can get complicated things, complicated patterns in space-time now, so this is space, this is time, so if I were to have the whole thing, I would have the space-time for the cellular automaton. If I could get a complicated shape, that would mean that I can get complicated shapes from very simple rules. This is sort of like this deterministic chaos and all that business. And so here's, for instance, one rule. I'm going to have zeros or ones. Okay? So the rule I want is something like this. Okay. If there's a 1, okay, let's do kisses and hugs. If there's a kiss, in the next stage, it's going to be a hug. Okay? No matter what these are. If this is a hug, and exactly one of these is a kiss, then you get a kiss here. If you have 2, you get 0. You don't have anything. Or you can have this. Okay. Now you start with 1 kiss. Everything else is this. Okay. Now what is the next stage? We keep reading. Okay. So to figure out this, I need to look at these neighborhoods. And it says that previously it was a kiss, which means that this has to die. It has to turn into a hug. This, you see, it has 1 kiss, 1 hug, which means that this is going to be like this, it's going to be like this, everything else is going to be hug still. Now you keep looking. So this is going to be like this. Now this has to be a hug because you have 2 kisses here. But this has to be, so this is 0 still. That's a kiss, that's a kiss. Okay. Okay, so what is the next stage? So now you go here, this dies, this dies, this is a hug, this is a hug, this is a hug, this is like this. Okay. Keep going like this. This, you see that's a 0 now, because of these 2. That's a 0, 0, 0, 0, 0, x. Keeps going like this. Okay. Now it turns out that if you keep iterating this, you get the Sierpinski carpet. The x's turn out to be Sierpinski. You know, it sort of like gives you the Sierpinski business. And in fact, it turns out that this is nothing but the Pascal triangle modulo 2. So 1, 1, 1. So in the middle, I put a 0. But then it's going to be 1, and then 2. So 2 modulo 2, I'm going to not count it. So that's that point. And then 1, 0, 3, 0, 3, 0, 1. See? And then 1, 4, 6, 6, 1, 4, 6, 4, 1. So I'm going to have zeros. Okay. Now you can take the Pascal triangle, look at it modulo 15 or 75 if you want. And that gives you something else. But somehow you see the Sierpinski business that we were looking at from a certain point of view is also related. It can be generated using this other thing. Okay.
So is Pascal's triangle also a dynamical system then?
Well, okay, so I'm sort of like stretching, of course. For me, yes, but typically when you're talking to someone and he says dynamical system, he means something like this, the sawtooth map, like you keep iterating one thing, or something like a differential equation. But if you ask me, even the axioms of math is dynamical systems. Okay, so it depends. That was an idea that I had that came to me when I was in grad school. I realized dynamics is before math. This is not that weird of a thing to think, but I don't have enough information and knowledge to justify it yet. Maybe in 25 years. Okay. You still have a couple minutes, I think. Yeah, 2 minutes. Anything else? So let me just say here, ordinary differential equations, now the time parameter is going to be not integers. It's not going to be discrete time. It's going to be continuous time. But you're allowed to do that. That's still dynamical systems. Yes?
Are there any references that you provide to find problems related to specifically dynamics, or?
Yeah, I mean, if you look at the Pessin and Kliman Haga book, there's a draft version of it under the resources. They are more focusing on dynamical systems, things like the Lorentz attractor, Fitzhugh Nagumo systems, and more math bio stuff. Yeah, yeah. Yeah, the cat map has nothing to do with a cat. It's just that one of the big Soviet mathematicians, very influential, Arnold, so he sort of was drawing this, but when he was drawing it, in order to describe how he was acting, how this map was acting, he drew sort of the picture of a cat, and that's why people call it the cat map. Has nothing to do with a cat, unfortunately. So this is a two-dimensional map. It's again in the paradigm of stretch and fold.
I think I saw this in linear algebra.
Say again?
Could this have been shown in my linear algebra?
Yeah. Let me just write it like this. So this is going to be acting on the square. This is also a notation that people use in dynamics. You go from the set to itself. Let's call it f. So f of x comma y is going to be 2x plus y comma x plus y mod 1. So if you know linear algebra, this is 2, 1, 1, 1. Okay. I could draw the picture as well, but I don't think we have time, so we have to stop. But this is sort of where sort of everything starts to open. Next week, we're going to start looking into something even more specific or more general, perhaps looking at how you're looking at it, or depending on how you're looking at it. Iterated function systems and say more nice things and fractals and all that stuff. Okay, thank you.